All right, good morning. So today will be lecture number 24. We'll discuss anomaly detection. But before going into that, there's quite a few logistical items I want to discuss. Firstly, about the final exam. As I mentioned before, there's going to be a final exam to every one of you who has chosen the option for a final exam. It's going to be a 90-minute exam. Usually a quiz 1 and quiz 2 was 75 minutes. So this is going to be a bit longer. It's going to be 90 minutes, 100 points. Very similar to before. It's going to be administered via Canvas, open notes, open books, and except for length of exam again, everything else is going to be the same. So the exam will be published on 4/22, which is basically next Monday. So you should be able to see it on your Canvas. Any of you who has chosen the exam option and who's not going to be able to see it, please let me know. I need to change it. Of course, you'll be able to see it, but it won't be available to you. That means that you cannot take the exam before May 1st, but you can see the fact that that exam is going to exist by next Monday. So materials are going to be everything from lecture number 1 to 26. Now in quiz 2, when I had said this, it's going to be lecture everything from 1 to how much ever it was in quiz 2. Most of the time, the materials after quiz 1 is essentially what I had quizzed you on. There wasn't anything before from quiz number 1, let's say, in quiz 2. But finals is going to be a little bit different. Of course, there's going to be more of an emphasis for all the topics that we have covered after quiz number 2, but you still will have questions from quiz 2 and quiz 1 as well. It won't be as blatant as quiz 2, where everything was from the materials that was there after quiz 1. I believe it was like after lecture number 7, I think after quiz number 1. This time there'll be a little bit more balanced coverage, but still more emphasis is going to be placed on anything and everything after quiz number 2. I think it was like autoencoders. Autoencoders and later was the portions that was not covered in quiz number 2. That is about the materials. Homeworks. Your homework 7 is due today. It's due on Friday. And for the distance learning students, it's going to be due Monday, the next Monday. This time, there's not going to be any extensions or late acceptance with penalty as well. I think I've mentioned this before. The reason being that Georgia Tech has a very strict policy regarding the reading period itself. So we are supposed to give you back the graded homework number 7 before the reading period starts, which is, I believe, on Wednesday. So our goal currently is to make sure that all students receive, in-person students, you get back your homework number 7 on Monday. You submit it this Friday, and you'll be able to get it on Monday. And for distance learning students, if you submit it on Monday, hopefully you'll get it back on Tuesday itself. I've talked to the TAs, and the homework numbers 5 and 6 will be given back this week. Hopefully they'll be given back before the TA officers, which implies that you'll be able to go and talk to them. If you have any concerns about homework number 5 and 6, you should talk to them. And even before that, any questions or any clarifications you have regarding homeworks number 1 to 4, let's say something was not graded or you had submitted it late, but you don't see it on Canvas, please talk to the TAs. I think you have to do this before the end of this week. The best thing is to go to the TA officers, or you can email them for a one-on-one discussion about grades. So again, the reading period is going to begin next Wednesday, I believe, which implies that by that time, everything regarding homeworks need to be sorted out. All your scores is going to be final before next Wednesday. All right. Yeah, in the red, again, no extensions or no late acceptance this time. So even though PACE, if it's not working, make sure that you do it as quickly as possible from today onwards itself. Don't wait until the last minute when you might not be assigned the notes. All right, regarding projects, the project report is going to be due next Monday. So it'll be very similar to the progress report that you uploaded. Essentially, anybody, the names, the representative names that are there on Google Sheet, I'll use that to create assignments on Canvas. So that means that you will upload your group materials. So there'll be one set of materials per group. It's not an individual. You're not writing individually your reports. It's going to be one group-based report. So in terms of what you'll upload itself, there can be two things, one of which is mandatory. The first one is the mandatory one is a project report itself. It should be in the IEEE style format, the one that you used in the progress report. We'll accept a maximum of 4 pages of content plus any number in terms of references. So 4 pages, everything all your content has to stay within those 4 pages. Anything after that, we probably might not read it. In terms of content itself, we're not making anything mandatory. The only mandatory thing that I want is individual contributions. So some of this I realize is a bit tangible and some of them is not tangible. So for instance, it's very clear who might have written what. So for instance, one person in a group might have written the introduction, another person might have written something like a related work or a literature review, another person is in charge of writing, let's say, the results. So these things are tangible. You should mention this, that person number 1 in the group has done this, has written this, and the other person has written that, and so on. Some of the things like who came up with certain ideas might not be as tangible. So ideally, you would have worked in a group, and this is going to be like a discussion process where you would have come up with the ideas. But of course, it's not. If you have pursued your own ideas, let's say you started off having 2 different branches within your project, and one of you decided to take one branch, another person decided to take another branch, and you have tried out different ideas within your own branch, I want to hear about it. So this is essentially where you'll talk about your individual contributions within the project itself. That's the only mandatory thing in terms of content. Apart from that, think of it like you're writing a paper, like a conference paper. So everything else has to be similar to like you need to have an introduction, something like a related works, something like a method section, results section, discussion section about what your results look like, what you could have improved. Let's say if you had like 3 more months of time or something like that, right? All those parts is up to you. There's nothing mandatory in terms of the content itself that you would have to write about. Again, maximum of 4 pages. You should keep the content within that page limit. Some groups who are working on like the fast SAM and efficient SAM, for instance, you could benefit by adding some kind of a project video or demo. In fact, that might be the easiest way to show your results. Instead of putting in a bunch of results and tables, let's say, if you're able to show us in terms of demos, okay, before it was like this, we did this work, and because of that, our throughput or our latency or something has increased or decreased in terms of latency by X amount, let's say. The best way to actually show that would be this kind of a demo or a video. So you're more than welcome to do that as well. But of course, this one is going to be optional. Not all groups require this. It could be like an optional part within your uploading materials. Maximum of 5 minutes. I'm just putting it here, but it's up to you in terms of the length of the demo or video you want to do. Ideally, it shouldn't go above 5 minutes, but if it does, it's fine. So similar to the progress report that you did, I'm going to create a Canvas assignment again by Wednesday, that is by day after tomorrow. So I'll use the same names that are on the Google Sheet. If you want to nominate someone else, please do so by today or tomorrow, so that I'll use that name to create a Canvas assignment for you. Any questions regarding the project, homeworks, or the final exam? All right, in terms of the grading logistics, because you had an option of choosing the project or non-project, there's multiple options. So 4803 section, you always started off with 60% assigned to your homework, 10% for quiz 1, 10% for quiz 2, and about 20% for finals. But some of you have chosen the project option, which implies that the 20% finals is now changed to a 20% project. Some of you have chosen an exam option plus a project option. I think there's 2 groups that have chosen this, which implies that you're going above and beyond. So you'll be doing like 120, you'll be graded for 120% essentially. So you'll have, think of your project as extra credit, which you're doing for like 20%. Some of you have chosen specifically or emailed me specifically about extra credit. That will be about 10% additional. I've already assigned extra credit assignments. So that should be about 10% of extra credit. So you'll be graded essentially for 110%. For the 8803 section, the grad students, you were always assigned about 40% of your total grade for homeworks, 10% for Q1, 10% for Q2. There was a 20% finals and a 20% project. But most of you have chosen the project option, only the project option, rather than the finals plus project, which was the original one, in which case you will be assigned 40% of your final grade that is going to be based on your project. That means that you won't be taking your finals. It's going to be all based on projects. Some of you have asked for extra credit as well, and again, there's like 2 ways of extra credit, right? It depends on if you have taken your finals or if you're doing the project option instead of finals, in which case it's going to be 40% plus 10%. Otherwise, it's going to be 20 plus 20 plus 10. Still, it's all going to come out to like 110% that you'll be graded for 110%. All right, so this was just about the logistics, about the grading. Any questions before we move on to the lecture for today? All right, so today we'll be talking about anomaly detection. Now, my original plan was to do self-supervised learning and active learning across today and Wednesday and do anomaly detection on Monday. But since you have already worked on anomaly detection in homework number 6, I thought it best that we cover a little bit about it today itself. Because even the best answer that you could have gotten in homework number 6 for the anomaly detection question is not really a good answer, because there's no way we can set up a good anomaly detection like a framework within a homework setting. So some of the results that you would have seen, even if you have train the best autoencoder network, you might not really get to know or get to understand what anomaly detection actually is. So hopefully I'll talk a little bit more about it today, and you'll get more of an idea in terms of what we mean by anomaly detection. All right, so anomaly detection is, the goal is pretty straightforward. We want to find rare events in normal patterns. So in number 1 over here is a microscope imaging of nanomaterials. So anything in red is basically an anomaly. It's not something that we expect within this image. And these things have to be segmented out because they are not normal. Image 2 here is basically silicon chip. Anytime there is any kind of a discrepancy in your chip that has been constructed, it has to be, it's not usable essentially. And if you put it within either a smartphone or a watch or a laptop, your device is not going to work as you want it to. So it's very important to have this kind of anomaly detection in chip making. 3, I think, is very straightforward. Everyone knows heart rate. There's P, Q, R, S. R is the big spike that you see over here. S is the small dip after R. So the region of this dip is basically what we call as S. This is a very standard heart rate for everyone, but sometimes what happens if you have arrhythmia or some kind of other heart issues, the S region is not going to be as well defined as the other parts within your heart rate. So this is an anomaly within your heart rate. This is something that has to be identified. Let's say you're wearing some kind of a watch, some kind of a monitoring device. It has to be able to understand the PQRS regions within your heartbeat, and it needs to say that the S is incorrect or it's not conforming to your normal heartbeat. So there is some issue. You might have to go to the doctor and so on. So this is a very important application within the idea of machine learning, where we have learned on normal data, but now we are presented with data that is abnormal or anomalous, and we should be able to detect it. Everything that we have done till now, supervised, unsupervised, everything is about basically training something and testing it on similar data. The only time we did not conform to that normality was when we talked about denoising autoencoders and variational autoencoders, and we'll bring that back essentially because those form important ways of trying to find these kind of anomalies. So just as a simple definition, anomalies are patterns in data that do not conform to a well-defined notion of normal behavior. So in the PQRS part, the P, the Q, and the R, the fact that there's this huge spike and a dip before it and the dip after it, essentially tells us that this is how our normal process need to look like, our normal behavior needs to look like, but then we might have an anomaly, something that does not conform to this well-defined notion of normal behavior. That is essentially what an anomaly is going to be. All of anomaly detection is generally based on the data process itself. So we have talked about this before when we talked about either GMMs or VAEs, but there is some kind of a data generation process that exists in nature. It's not something that we can control, it just exists. So that is a stationary process, which is P of n. So anytime there is some kind of a different process that has led to a particular abnormal data or anomalous data, then we say that we have a different process P of A, which is not the same as P of n, and this is when anomalies have occurred. Again, examples like arrhythmias in ECG is something that we saw. If you're doing some kind of a monitoring credit card transaction, some kind of a fraud, this is very important, of course, in like financial transactions and financial institutions, which should be able to detect these frauds in your credit card transactions. Defective regions in an image, similar to the microscope image that we see over here, we should be able to detect these kind of anomalies. So let's start by looking at a simple problem setup of what anomaly detection is and how we'll be able to detect these kind of anomalies. We'll start with a very simple definition. X is essentially our image in the pixel domain. Z2 means that it is an integer of R2, which is basically your X and Y direction or axis. There is basically a set of pixels that go from, let's say, 0 to 255, which is a uint8 image. And all of that are basically belonging to this X. So S is an image defined over the pixel domain. C is a set of pixels, and S of C corresponds to the intensity. So whenever we say image, right, so there's like three things associated, actually four things associated with an image if we are considering RGB. But disregarding the color portion, we talk about X and Y, which is essentially the positioning of my pixel and the intensity of that pixel itself, which is given by S of C. Now our goal is to basically locate this kind of anomalous region. So think of this as a very simple segmentation that we do on top of images in order to describe where our anomalies are going to be based on some statistic that we are using. In this case, the statistic that we are going to be using is S of C, which is our intensity value. Our goal is to estimate this omega of C, which is essentially this kind of a binary mask, and that is going to be 0 if pixels fall in the normal region, and it's going to be 1 if it falls in the anomalous region. It's basically this binary mask. So all these regions over here, for instance, are anomalous because they have the value 1, and you see the color intensity. White is essentially 1, and black that you see everywhere else is basically has an intensity of 0. A very simple way of thinking about how we can do it is by looking at this kind of stream of data, right? Let's say you have some kind of a regression algorithm. This regression algorithm is, this looks like a sinusoid, right? Or at least as sinusoid as possible. So based on this kind of a regression algorithm, based on all the points that I have generated up to a certain point, X of t, let's say, is a time domain signal. This X of t, where t goes from t0 to some kind of a, let's call this as t11. So until this point, you have 11 samples that you have derived from t is equal to 0 to t is equal to 11. And our goal right now is to see which of these samples is anomalous, right? So that is the entire goal of anomaly detection. So here X of t are random realizations of some PDF which is given by phi naught. Again, phi naught is your data generating process. Your P of n that we discussed before is this phi naught. Our goal is now to detect these outliers or anomalous samples. So the best way for us to do it is by considering that statistic. For images sorry. So for images, that statistic is going to be intensity. So given a particular intensity, I can say that that intensity value, if it is greater than something, then it is going to be anomalous, right? That is like the simplest way I can create this kind of an anomaly detection algorithm. Same thing in this stream of data as well. I say that if x of t, let's say the highest point is this, which is, let me call this 5, let this be 6. If I say that any data point that exists above 6 is anomalous, then that is a rule that I'm considering. In that case, the statistic I'm using is x of t, and the decision rule that I'm using is 6. So anything that is greater than 6, which is my decision rule, and x of t is the statistic that I'll be using in order to say if something is anomalous or not. Again, what I did was a very simple way of doing it, which is I just took the max value and said max value towards the left hand side and said that this was anomalous. I know that this here is anomalous because it's in a different color. It's a completely contrived example, so it's very clear in this case. But in most cases, it's not as clear what the statistic or the decision rule is going to be. You need to create some kind of an adaptive threshold or some kind of a confidence region in order to say if something is anomalous or not. All right, so this is essentially saying that we created some kind of a regression model on the entire data that we have. We have monitored this data from x0 to x11, and we have constructed this kind of regression model. And then we have said this decision rule. If s of x, which is our statistic, is greater than a certain gamma, then we can say that this particular data point that exists at t is equal to 9, let's say, is going to be anomalous. The decision boundary here is gamma. I think here I used 6, but if you want to generalize it more, it basically becomes this kind of a gamma variable. Right? So in terms of hopefully the problem setup is quite clear. We have a data point that does not conform to normality, and the easiest way that we can define it is by getting some kind of a statistic and then creating a decision boundary based on that particular statistic. Now, the goal for us today, after we do the performance metrics, when we come to the statistical reconstruction methods in GradCon, is to construct the statistic and this decision boundary. Because in these contrived examples, it's quite straightforward, but as you have seen, maybe even in homework number 6, when you did that anomaly detection in the last question, it's not straightforward at all, how we get that statistic and how we can construct our decision rule. All right, before that, let's look at a few important things. Performance metrics. Again, when we talked about classification, regression, segmentation, performance metrics is something that is very important for us to look at, because that is how we decide whether a statistic and a decision boundary is actually good or not, right? And most of these performance measures is something that you would have seen already. TPR, which is true positive rate, and FPR, which is false positive rate. The difference from when we looked at this for classification is what is here up top. Number of anomalies detected. So when we discussed within classification settings, it was basically the true positives, right? The number of examples that were correctly classified as the class, as their labeled class, is what was up there in the top. But in this case, when we talk about TPR, it's about the number of anomalies that are actually detected and the number of anomalies that are in fact present within my pool of data. Let's say if I have a testing sample case, then if the number of anomalies detected and number of anomalies may be different. So one question you might expect in your finals is basically similar to the confusion matrix that we saw back in, I think, exam 1 when we had it for classification. But in this particular case, you can have a combination of anomalies as well as the classification results essentially. And you can be asked what is the TPR for anomalies versus what the TPR is for classification, and so on. Same thing with FPR as well. The top part is the number of samples detected, and the number of normal samples. Think of this as a binary classification. Something can be either a normal sample or it can be an anomalous sample. So in fact, this can be simpler than the classification setting. In a multi-class classification setting, you might be given like 10 different classes, and the confusion matrix will have like a 10 cross 10. Right? But in an anomaly detection setting, it's going to be very straightforward. It's going to be a binary classification, either a anomality, or it's a normal sample. But you can get your TPR, FPR based on very similar principles here as well. And other things as well, your FNR, TNR, precision and recall, everything that we had discussed before applies in this case as well, but more for a binary setting. And the difference, of course, is your labels is not class. Your labels is now whether something is a anomaly or not an anomaly. As we have seen before, your TPR and FPR is in fact now dependent on the statistic as well as gamma. Statistic is basically, think of it as an algorithm. So you have designed an amazing autoencoder that is giving you a very good statistic of your result. Now the goal is to construct a gamma. Look at how this gamma is now going to affect your true positive and false positive, right? So there can be two possible gammas here. The one in the gray, I think you can see the color there, yes. And the other one, the bottom at the golden one. Depending on whether you choose the gray gamma or the golden gamma, your number of anomalies, detected anomalies is going to be different. For gray, there is just one anomaly, which is this one here, while for the golden one, there's two anomalies, which is the one here, along with the one that was there. So gamma is going to be a very important parameter when you're going to be discussing this TPR and FPR case. Changing gamma is going to change all the performance metrics that can exist. So it's we need to take that into consideration as well, right? One way to think about it is by saying that I can't look at TPR and FPR by itself. I need to look at a combination of factors of TPR, FPR, which basically leads me to accuracy and F1 score. Both of these measures are not just dependent on one FPR or TPR, but they're basically a combination of the two. Hence, they can be good, because that might mean that gamma has been taken care of when you're discussing the TPR and FPR together. A better way to try to understand this trade-off, or to make sure that gamma is not as impactful from your algorithm perspective, is to go back to the AUROC curves, the area under receiver operating characteristic, those kind of curves, which essentially means that you create these curves across different values of gamma. Again, this is more of a recap, but let's say you have FPR on the x-axis and TPR on the y-axis. You, for different values of gamma, let's say if you have 0.2 and 1.6, which is somewhere over here, your 0.2 is FPR and TPR is 1.6. For a particular value of gamma, you will be able to get this kind of TPR and FPR. So for that gamma, it is basically a model, right? So this here is one particular gamma 1. Similarly, this here is another particular gamma 2. So based on different values of gamma or your decision boundary, you can have multiple statistics of FPR and TPR, and you can use them in order to construct these kind of AUROC curves. Again, we have seen this before. This is exactly what we did back in lecture number 6, I believe, when we looked at performance characteristics, performance measures for classification. So different algorithms. So forget the algorithm, the name of the algorithm themselves, it's not as important, but one way of comparing between these algorithms, or you can think of them as statistics, S1 of X, this is S2 of X, and so on, right? So one way of comparing between S1, S2, S3 is by looking at area under these curves. The best area, of course, is going to be here, it's here at 1. So it's basically a rectangle. It's a 90-degree line that, or the line here is going to be parallel to the x-axis, and that is your best possible algorithm that can exist. So this is where your AUROC is 1, and everything below that is your S1, S2. And higher this AUROC, or the area under these particular curves, the better your result is going to be. Any questions about the performance metrics? So let's move on to the next part, which is the anomaly detection settings. So we'll talk about two settings, which is semi-supervised and unsupervised setting. But there are, in fact, three different settings. The last one, I think, is more, it's more trivial based on the fact that we have already learned the supervised learning. I'll talk about that a little bit, but we won't go deep into that. So whenever we talked about this kind of classification, segmentation, or regression, right, we were provided a training set, and we use that training set to convert it into a training set and a validation set. And once we had a training and a validation set, we then used it in order to, we then used our performance measures to see how good our algorithm, our trained algorithm was within the testing set. So this is something that we always had, these kind of splits. And the idea of unsupervised or supervised learning came from the fact that if the labels existed or not for the training set. And by labels, I mean if it's classification, then that means that the label would be, let's say if it's classifying between cats and dogs, then every single data point needs to have the label of a cat and dog. So that is how you would have defined unsupervised and supervised. In anomaly detection settings, this is a little bit different. Again, our labels in this case are not just the cats and dogs, but I want to know if it's an anomaly as well. So basically, when you are trying to differentiate between cats and dogs, let's say you're given an image of an elephant. So this is an anomaly. Or you might be given an image of a zebra. It's an anomaly. You don't need to know that these are elephants or zebras. You just need to know that they're anomalies. So that is like a third class that needs to exist within your cat-dog differentiation, which is that if a certain image is an anomaly or it's not an anomaly. And based on that, you have all these settings, and that's where the label data assumptions come from. So in a semi-supervised setting, only normal training data are provided. That is, no anomalies in your training set. In other words, for instance, let's say you're taking X-ray images, you're taking data set of your lung, your pulmonary, some kind of X-ray images until mid-2019. In all these cases, you'll have access to pneumonia, you'll have access to other kind of lung diseases, right? But you'll never have access to something like COVID-19, pre-2019, pre-mid-2019. So any kind of data that you can get later down the line is something that you would have to detect as an anomaly. So that's where essentially you'll be able to say that, oh, COVID-19, this is a novel kind of lung X-ray image that I'm seeing right now, because it was not part of my training set at all. So this is in fact a semi-supervised setting where you know for a fact that all your training data is normal, that there has not been any kind of an anomaly within your training data set. Everything is normal data. Unsupervised, on the other hand, your training data can have both normal or anomalous data. In a way, we say that TR is provided without label. And again, I want to stress, label here does not mean pneumonia or COVID-19 or cat and dog. It's presence of the anomaly or not. So if your training data is provided without label, then that means that maybe some of the training data is anomalous, maybe some of the training data is normal. While in the semi-supervised setting, only normal training data is provided. So you know for a fact that if it's within your training data set, it is normal set of images or normal data, and your goal then during test time is to say whether something is anomalous or normal. Supervised setting is a very trivial case. Both normal and anomalous training data are provided, which implies that you are given your normal data and your anomalous data. In other words, you can actually construct supervised learning algorithms at this case. It's a very simple binary classification setting. You don't even need to have, even within ImageNet, let's say you have 999 classes that are in distribution. You're considering that 999 classes are normal and one class is abnormal. So basically, you've taken a 1,000 class data set and converted into a 2-class binary data set, where every single image within that 999 classes is going to be labeled as normal, let's say 0, and the anomalous class, the remaining 1 class, is going to be anomalous, which is going to be 1. Right? So you've converted a very big 1,000 class data set into a simple 2-class data set, and you can now go back and do any kind of supervised learning algorithm that we have learned. So supervised setting is a more of a trivial setting where we have access to all labels in terms of whether it's an anomaly or not within the training data itself. So then it's a goal. The goal is basically how best can you train your algorithm. Everything that we learned in terms of class imbalance and all those comes into picture, and you'll have to create a good supervised algorithm. So we won't be discussing about the supervised algorithm itself. We'll have more slides regarding semi-supervised and unsupervised. Any questions about the setting itself, what the difference is between these two things? It's very important to differentiate them from the classification settings and to know what exactly the difference is. All right, so yes, question. So it is, so again, you're thinking of that from a supervised learning setup. So you're thinking that you need a loss function where you need to know something is anomalous or versus not anomalous. Think of everything that we did within unsupervised learning, that will be in the semi-supervised learning setup. So we are gonna, I mean, a simple way of thinking about it is that I would have overfit my network or my GMMs towards the training data, and anything that doesn't conform to this overfitting is going to be anomalous. That's one of the simplest ways of thinking about how semi-supervised learning setup is done in anomaly detection. We'll discuss more when we talk about the methods. I think hopefully it's going to be clear. So one thing that we know in semi-supervised learning setup is your X is always coming from a single normal data generating process, which is phi naught. And if you were to construct a statistic and look at the threshold, it is always going to be less than that particular threshold, which is T naught. Now again, this is probably one of the most practical assumptions that exists. You always assume that the data you have is going to be normal. Again, going back to that case of COVID-19 versus pneumonia or other kind of data sets, any data set, lung data sets that you see before 2019 has no case of COVID-19 essentially. So anytime you're learning some kind of an algorithm on those data sets pre-2019, you know that none of the images, none of the people in those studies have been afflicted with COVID-19, right? So now it's vast majority of our data sets that exist are basically like this, where it's going to be a normal data set. Again, medical is probably a simple way to talk about this, but even autonomous driving data sets, you don't have as many, let's say, accidents within your training data, and even accidents themselves are going to be so varied, right? Like if you look at the popular, I don't know if popular is the right word, but the more publicized accident that Tesla has, most of them are very different from each other. Even though we can think of them as all anomalous, there's still going to be different classes of anomalous within themselves, where if it has looked at a particular accident and has taken care of that accident, let's say an algorithm that was learned in 2022, 2023, there was a different kind of an accident. So it has to look at that and say that the fact that there was an accident means that it is something anomalous that it has not encountered before, and it has not worked well at that particular point, right? So this is probably one of the it's a very practical setting, and probably one that whenever we talk about anomaly detection, this is essentially what we'll be discussing, which is the semi-supervised anomaly detection setting. Again, anomalous data is very difficult, costly, and sometimes it's impossible to collect. Any pre-2019 data sets will never have COVID-19 because it did not exist. So it's impossible to collect such anomalous data. And training examples in the training set may not be representative of all possible anomalies, of course. And that's why this is a good way of thinking about it. We have to overfit, or we need to construct a model for our normal data, and then hope that any kind of anomalous data that is going to come in is something that we can detect down the line. So one way of looking at it is the density-based methods. By density-based methods, it's the logistic regression, it's the variational autoencoders, it's the GMMs, essentially any kind of generative modeling where we consider a density, that the data that we have as some kind of a density is essentially these kind of density-based methods. So we want to monitor these kind of log likelihood with respect to the data generating process, which in this case is phi naught. So during training, our goal is to obtain the data generating process. Again, the goal of GMMs is to put these kind of Gaussian models on top of the data, right? We don't know the data generating process itself, but we estimate it based on a multivariate Gaussian distribution. Same thing with VAE as well. We assume that there is a data generating process, and based on that KL divergence, P is the data generating process, Q is some kind of our estimate of that data generating process. We put a simple KL divergence between them and say that P should now be equal to Q, or we are estimating this P given a small amount of data and getting our Q value, which is essentially our density. So our goal is then to create some kind of a likelihood function, which is log likelihood function, which is log phi naught x of t, and then monitor this kind of a log likelihood function across different values. Again, looking back at that simple sinusoidal signal, at t is equal to 9, there is going to be some kind of a discrepancy, an anomaly, which implies that my log phi naught x of t, this would have exceeded a certain value which was 9, which now implies that there has been some kind of an anomaly. So this here, this log phi naught x of t, is the S of x. It's the statistic that we are obtaining out of our, we are estimating from our data generating process and using that within the threshold framework. Again, the gamma and Sx by itself are methods. I'm just using 9 over here. T is something that we have to set ourselves as well. So this falls into the umbrella of semi-supervised learning. And a very important part here is to try to understand the assumption, which is that normal data occurs in high probability regions within a model, while anomalies occur in the low probability regions of a particular model. So given a model, if you have this kind of density, right? So this is like a Gaussian distribution. So if I look at level curves, this is very dense versus this is not as dense. So this is like level curves. This is like a Gaussian distribution I'm looking up from top. So in this particular case, most of the high density regions, which is somewhere within, this is where the normal data resides. If I have some data point that is greater than, let's say, 95% away from the center, the standard deviation is 95% away, then essentially that might be an anomaly. Again, this is a very simple observation that we are making, but this is the assumption that leads to the entire density-based methods within the self-supervised learning framework. The problem, of course, is that it's very challenging to fit these models on high-dimensional data. Again, when we look at neural networks, our latent representation can be something like 1024, 4096. I think in AlexNet it was 4096 before the, like one layer or something before the final fully connected layer. It was about like 4096 data points, right? Which implies that you need 4000 multivariate Gaussians that need to be fit on top of it. And it's very, very hard then to construct basically T. On this kind of data. So it's very challenging to do something like this. But it does have its advantages, which is that it's probably the safest way because we have a very grounded assumption, which is that after a certain greater than 95%, let's say, our values are going to be anomalous. And it's a very explainable, it's a very explainable decision as well. You can tell someone that you're 3 standard deviations away from normal. Let's say in fraud detection in financial transactions, if the transaction that you have done is 3 standard deviations away from what you normally do, it's easy now to construct or explain this kind of a decision from a model. So density-based models are a very safe method for doing anomaly detection, but they come with their own challenges as well. All right, next is the unsupervised anomaly detection setting. Unsupervised anomaly detection setting is we don't have access to the data generation process, or we don't know if a particular data point is, let's say, anomalous or not anomalous. So the assumption that we'll start with which is not a good assumption, actually it's an incorrect assumption, is that anomalies are very rare with respect to normal distributions within the data. And we'll use this to construct our methods. The simplest method that we can construct is distance-based methods. Again, our assumption, an incorrect one, is that most of the anomalous data within our training data set is going to be different from our normal data, which implies that if I have this, and then this is far away, then it's going to be different, right? So this and this is far away, this here which is far away, this here is far away as well. Again, this is all within the training data. When we were thinking about the density methods in semi-supervised setting, we would have learned this density and then say that this particular data point is away from this density, hence it's anomalous. But in the unsupervised case, we already assume that a density exists which belongs to the normal data, and the abnormal data or the anomalous data is basically away from our normal distribution. Again, this is an incorrect assumption because all of this is now part of our training data set. This is now again based on S of x. So knowing that there's a good S of x or a statistic available, then maybe this assumption is correct. But there's no way of us for knowing whether our statistic that we have derived, let's say the latent autoencoder representation space that you derived in homework number 6, whether that is a good representation, whether that is a good statistic for saying if something is normal or anomalous. So in this case, this in fact could be normal data, while this could be anomalous data. It's just that your representation space has decided that this is the best density and given a particular statistic, which could be incorrect. So it's not always a good way, but sometimes there is no other choice when it's an unsupervised setting. And this is where you can come up with good measures, good distance measures. L2 distance is not a very good measure when high dimensional representation space. We have already talked about this, but Mahalanobis distance is a much better distance when we are discussing about the representation space, because you take into account the covariance matrix, which is the data generating process itself, in order to construct these kind of distances. There are other kinds of distances that we are not going to get into, which are called geodesic distances. Geodesic distances, which basically are these kind of manifold distances in a higher dimensional representation space. It gives you, it basically tracks the manifold, or it tracks the representation space and takes distances on top of that representation space rather than these kind of convex distances, which are Mahalanobis or L2 distance, which slice through your representation space. Another method is isolation forest. In the very beginning, I think lecture 2 or lecture 3, there was this thing called random forest. It was one of the classification methods, but at the time I said that we won't discuss too much about it. You should just know that it exists. So basically, random forest, or in this case, is the isolation forest that we'll be using. A very simple way of describing it is basically partitioning your data. So start by taking one dimension, which in this case is we call component x1, which is, let's say, the x-axis component, and start by just dividing this x-axis component. So in this case, you have just divided this entire thing and converted into 2 different data partitions. And within these data partitions right now, you'll have 2 different, each element within each data point within these partitions can belong to one of these 2 different clusters. Do the same thing across different partitions. So you have this one partition, you have another partition. So basically now your one thing has now been converted into 4 different parts. The goal or the hope is that anomalies lie separated from other points, essentially. Again, this is very similar to the distance measure that we saw before, except that it's more of a binary search algorithm rather than a complete something like a bubble sort search that you would have done with respect to the distance-based method. This is a much more computationally inexpensive method of trying to find what your anomalies are going to be. And again, this is the binary tree or the random forest is also a very similar classification methodology that we use. Any questions regarding the setup itself before we move on to the methods themselves? All right. So till now we have discussed the settings, the performance metrics, as well as the problem setup. Until this point, we just assumed that we have this Sx and gamma. Now the goal in the next 2 to 3 parts of the lecture is to construct what this S of x is going to be and what this gamma is going to be. So let's start with the simplest one, which is Sx. Let's say on the one-dimensional data that we have, Sx is pretty straightforward. It's basically the statistics x of t, the one that we measure. If it's heart rate, then basically we are just measuring our heart rate. The signal at every single instant is going to be our statistic, very straightforward, right? But when it comes to more complex data, something like images, Sx is not as easy to understand. So for instance, let's just say the simplest Sx that I can find is this patch. Let me say that every patch within my image is the statistic that I'm using. So let's say this is going to be like an 8x8 patch, and this 8x8 patch will now be, let's say these are all normal patches. Let's start by using a semi-supervised setting where everything is going to be normal patches. Our goal is now to fit this kind of a phi naught that is going to describe these kind of normal patches that exist within my training data set. The problem with doing something like this is that the patch by itself is not a single number like you would have in heart rate, right? So this is an 8x8 patch, which implies that it's a 64x1 vector, and 64x1 vector is not it's not easy for us to analyze it and say that if it's greater than or less than a particular threshold. We need to convert that into a single number, right? The problem, of course, is that the pixels themselves are not decorrelated. I can't just take one single pixel and say that, oh, this is a median pixel, this is greater than something, this is a mean pixel that is greater than less than something, because all data is correlated. When we talked about like GMMs and logistic regression, one of the main assumptions that we made was about this thing called IID, which is identical and independently distributed, which essentially meant that each dimension within your multivariate distribution is independent. In other words, the 64x1 vector, the first element of this vector has nothing to do with the second element of this particular vector, is essentially what an IID distribution means in this setting. But we know it's not true, right? Look at this pixel. More often than not, the next pixel, the next 3 pixels surrounding it is going to be very similar to that particular pixel. So in logistic regression, when we had this joint distribution P of x1, x2, x3, and so on, we use this IID assumption, this independence assumption, to convert that joint distribution into a set of marginals, into a multiplicand of P of x1 multiplied by P of x2. We can't do that in these kind of image patches because there's a lot of correlation that exists. The next slide is basically showing those kind of correlations. This is between, let's say, pixel number 1. When you take 8x8 pixel patches across the entire data set and convert it into a covariance matrix, this is basically pixel number 1, this is our pixel number 2, pixel number 3, and so on. And this is the correlation between pixel 1, 2, correlation between pixel 1, 3, and so on. As you can see, it is highly correlated, and this is not what we want when we are trying to put some kind of a GMM directly on top of the pixels. We cannot put GMMs directly on top of the pixels because of this kind of a correlation that exists within the data process itself. I'm showing this with images because it's quite easy to see this within images, but this is true even within your heart rate or any kind of 1D signal as well. Generally, there's going to be some kind of a correlation between, let's say, T1 and T2. Right? If this is T1, if this is T2, these two are going to be similar to each other. Right? So it's harder to assume this kind of a decorrelated independent inputs when it's all part of the same data generating process, when it's being done sequentially. So the way we start thinking about this is, I've used this word before, which is manifold, but I don't think I've ever talked about it or explained it. It's essentially what is happening is that within, let's say, an AlexNet, 4096 cross 1 vector, so we are in a 4096 dimensional space. A manifold tells us that most of the data, 1 million data points that exist within the ImageNet dataset, you don't need all 4096 dimensions in order to represent them. Maybe there is a much smaller, let's say 100 dimensional subspace that can exist within the larger 4096 dimensional space, where all these kind of 101, like 1 million images reside. And that idea is essentially what we mean by manifolds. It also implies that these patches all exist together, similar to each other, within this kind of a manifold that may exist within my neural network, like a high dimensional representation space. Again, each point here, when we were discussing before, we were talking about the correlation between these small pixels within the patches. Right? Now, when we discuss that all of them live close together within this manifold, we are talking about the pixels themselves, sorry, the patches themselves are now similar and are stay next to each other within this particular manifold. We didn't talk about that before. We were talking about the pixel correlation rather than the patch-based correlation that can exist. So what this means is that patches can be described by very few latent variables rather than the entire 4096 latent variables that can exist. So this tells us that if you have some kind of a CNN architecture and in the middle, let's say some kind of a latent representation space that can exist at this particular point, it's a good assumption to make that all the patches or all the images that exist within our dataset are live closer within this particular manifold, that this manifold here is going to exist at some latent representation space, and all my data points are going to exist close to each other. When we did this idea of nearest neighbor thing within the explainability, like when we did it on last Monday, we were using this exact assumption that in the final fully connected layer or some kind of a latent representation space, the images of similar classes, it doesn't matter if the dog was looking to the left or the right, it's still the dog. Hence, all of them live close together in the final fully connected layer than they do in the initial layers, right? So that was an assumption that we had made. It's the exact same assumption we are making here as well, except that it's a little bit more rigorous. We are saying that there is a statistical model and there is a manifold, and this particular manifold has all patches or images that are close, that live close within this particular manifold. So latent representation of similar patches live close together within this particular manifold. So based on this, the simplest statistic that we can get is MSP. In fact, this was the first paper that came out in 2016 that talked about this idea of out-of-distribution and anomaly detection for deep learning for neural networks, which was a baseline for detecting misclassified and out-of-distribution examples in neural networks. So this essentially was, the method itself was called maximum softmax probability. So given a certain logits, you just calculate the softmax probability. And if the softmax probability, so MSP, is now your S of x, which is your statistic. If it's greater than a certain threshold, usually the simplest thing that they did at the time was 0.5. So if it's greater than 0.5, then that means that it is a not an anomaly, versus if it is less than 0.5, then that means it is an anomaly. So S of x is nothing more than your softmax probability. This could be one method for constructing your statistics within deep neural networks. You can't do the GMMs and the k-means clustering or random forest on these kind of 1 million data points. Hence, you would have to use a neural network. And within this neural network, the way you would get your statistic is by using something like maximum softmax probability. Of course, there are better methods that are based on these latent representation, but it's quite beyond the scope of this class. So the simplest method is MSP, which is maximum softmax probability. And using that, you can say this is the simplest statistic. If it's greater than something, then it's a normal image. If it's less than something, then it is unfortunately an anomaly. This also gives rise to this idea of in-distribution and out-of-distribution. So whenever you have, if you've read papers and you see this particular set of letters occurring together, which is OOD, it implies out-of-distribution, and it's a very important research field, which is detecting if something during your test time, if it's not something you have looked at during training, then it's not something that you should trust. The prediction is not something that you should trust. And it's very important that you recognize or you detect the fact that your testing sample is out of distribution rather than something that you had trained on before. All right. Next, we look at two things, which is reconstruction methods and GradCon, which is a gradient constraint methods together. So reconstruction-based methods is exactly what you did in homework number 6, which was an autoencoder. Our goal is to fit some kind of a statistical model to the observation to describe some kind of dependence and apply anomaly detection on the independent residuals. So residuals was the error that you had, and our goal was to apply this kind of or to see if anomalies and normal data can be separated based on these independent residuals that could be detected. So you need this kind of a model M. In your case, it was an autoencoder to encode and reconstruct normal data. Again, the goal then is to consider the latent representation is the most important thing here. You want to construct a latent representation space based on encoding data, and the encoding and decoding together is going to give you this kind of a model M. And you'll assess the error S, the residual between the reconstructed output and the input, and based on that residual, you're going to say if a particular data point is good or not, essentially, or if a particular point is anomalous or not. So we've looked at autoencoders before. Essentially, you have an input layer of neurons, and given a certain input, you have a hidden latent representation, and then you have the output, the reconstructed output. The goal is to make sure that your S1, I probably should have put a cap at all these points. So your S1 cap minus S1, S2 cap minus S2, and so on, what the error is among all these residuals, among all these outputs. We've also talked about the training part. Simple case is the reconstruction, the mean square error between the input and the reconstructed output. So there were two parts of your question in homework number 6, where the first part was showing you on a simple autoencoder. By simple, I mean that you were only training based on this MSE loss, but then you were asked to regularize as well. And we said that regularized autoencoders are better in terms of trying to see if something is anomalous or normal. As I mentioned at the start of the class, it's not easy to set up this kind of a problem in homework. So even with the best trained model, you might not have been able to see that there is going to be some kind of a difference. But ideally, what you should have noticed is that the training histogram, the error would look something like this, and the testing histogram, or the anomalous histogram, would look maybe something like this. So it's like, think of it as a shifted Poisson distribution rather than a normal Poisson distribution, which would have been there on red. This is ideally how your anomaly detection settings are going to look like when you have a very well-trained network on data that actually is normal and that is anomalous. But again, it was not possible to do it on a small scale like we did within the homework settings on these large-scale images, because the network has learned most things within the normal and the anomalous data. But the goal in regularization is, in fact, to do some kind of constraints. And this is where what I was talking about earlier comes back into picture, which is that by adding some kind of constraints to my activations, I can now say I can now use a statistical model to differentiate it rather than errors directly. So in this case, if I'm encoding 5 and 5, let's say I have constrained my latent representation space to have 3 Gaussian peaks. But then I'm putting an anomalous 6 image through the through the network, trained network. What I notice is that the representation space will only have 2 peaks instead of 3. That means that I can just finish fitting my latent distribution just using 2 Gaussians rather than 3 Gaussians, and that would be sufficient. And this tells me that anomaly now exists. Again, I'm not looking at the error itself. What I'm looking at is the constrained activation that I have created. maybe the reconstruction error in my training is higher. Like if I had not put a particular constraint, then my reconstruction would be something like 0.72, let's say. But since I've put a constraint, my reconstruction is going to be 1.3. So my original goal of training a good autoencoder has not happened, but I now have a better way of representing my anomalies based on this peak. And that is exactly what you did with the regularization as well. By adding a regularization, you created problems for the learning process. Your error does not go down below, let's say, 1.3 with regularization, but it would have gone down to 0.72 without regularization. But by adding these kind of constraints, you now have made these kind of peak-based activations where instead of having three peaks for normal data, you'll have 2 peaks for anomaly. So this is the main idea of this kind of constrained representation space. There's a lot of papers that exist which try to constrain your activations. Your VAEs, in fact, is a constrained representation setting where you're saying that the latent representation has to be normal 0, some kind of a sigma square. It has to be a normal distribution with a single Gaussian distribution in the latent representation space. There are other kinds of constraints as well, which is gradient constraints that we have seen across this course. When we talked about the backpropagation itself, we use gradients as this kind of an intelligent methodology for training. You could have had any kind of an update. WT plus 1 could have been WT plus 0.1 or 0.2 or 0.3 or 0.4. There could have been an infinite number of updates that we could have done. But then gradients gave us an intelligent way of saying that, okay, I want us to go towards the local minima or the minima of my loss function. And using that, I'm going to update my weights and my bias, right? So gradients was an important way of constraining my steps or my updates. Same thing in explanations as well. By backpropagating the gradients or the negative of gradients or loss gradients, you can essentially have different kinds of explanations. So another constraint is by constraining these gradients. The next few slides, I'll leave it up to you, which is the idea of GradCon, but it won't be there for the exam. The method itself won't be there as part of the exam, but the idea is very similar to the gradient constraints, which is that instead of constraining on the activations, I constrain on the gradients. So essentially, I'm going to create a loss function with respect to the gradients and say that if my gradients are diverging by a large amount, then you need to penalize these data points more based on these gradient constraints. And using those constraints, you can show that it's better than activation constraints. In fact, you can do it across like VAEs, you can do it across convolutional autoencoders or VAE autoencoders and so on. So in most cases, gradients are a better constraint than your activations themselves. So anything after, I should have probably put this in red, anything after slide number 48 is not going to be part of your exams. It's more of a FYI only. The motivation is important. The motivation of what gradient constraints are, you might be asked in the exam, which should be covered until something like slide number 47. All right, so that is the end of today for anomaly detection. On Wednesday, we'll start with learning paradigms. Specifically, we'll start with self-supervised learning. And on next Monday, we'll cover active learning. And that should be the end of the semester's lectures.